Let's take a look at problem number 7. So here we're given two graphs, and your first job is to describe what's going on, considering this to be the motion of a car. So just pause the video and you can write a little bit about what's shown with each of these graphs. You don't have to write a full sentence, doesn't have to be a paragraph, just a couple notes to describe the motion. Now anytime you look at a graph, one of the first things you want to look at is what's being plotted. These are both velocity versus time graphs. These aren't position versus time graphs. It's not telling you where the object is. It's telling you how fast the object is moving and in what direction the object is moving. Positive, the object is moving forward. Negative, the object is moving backwards. All right, so we got car A here, and with this being a velocity versus time graph, you can see that the velocity is constant. It's moving at 15 meters per second the entire time. And since it's not speeding up or slowing down, and since we're only looking at one-dimensional motion, we assume it's not changing direction, we can say its acceleration is equal to 0. So I would write constant velocity, acceleration equals 0 meters per second squared. And feel free to add to whatever you've written. What's happening with car B? Well, this car starts from rest, and speeds up to 15 meters per second in these 4 seconds. And so it has an increasing velocity, and it's speeding up, so it's a positive acceleration. So we'll say it's speed increasing with a constant positive acceleration. Now let's talk about, try to visualize what's happening here, right? So let's say we're in car B. Let's say you're late to school one day, and you stopped at a red light, and you're in a hurry, and the light turns green, so you, the driver, or whoever's driving, floors it and speeds up from 0 meters per second to 15 meters per second in 4 seconds with a constant positive acceleration, okay? What's car A doing? Let's say car A is approaching the same light that you're at. You're stopped at this red light. This car A is approaching the red light, and here is a savvy driver. This driver checks the cross light and notices that the cross light just turned red. So he knows that his light is about to turn green. So here, this driver takes a chance that doesn't even slow down and just happens to time it right that the instant light turns green, he's already going through the intersection at 15 meters per second and maintains those 15 meters per second of speed for 4 seconds. Now, drivers and future drivers, this is a horrible idea. This is how accidents may happen, but this driver lucked out. Okay, so you're visualizing these two cars, right? We're in car B that speeds up from 0 to 15 meters per second, 4 seconds. This other car, in those same 4 seconds, is traveling at a constant 15 meters per second. So in your mind, visualize which car travels the larger distance in the same time. Pause the video if you need to think about it. Okay, so hopefully you've thought that car A is going to go farther. And if you didn't, well, let's go through why it should, right? Car A, when time equals 0, is already moving at 15 meters per second and maintains that speed. Whereas car B, the one we're in, starts at rest. And in those 4 seconds, eventually gets to 15 meters per second. So at every instant of time, this car is moving at a slower speed than this one, except for the very last moment in time, the 4 seconds. And so there's no way that car B could possibly catch up to car A, and certainly won't even go as far. So we're expecting car A should go farther, car B should go a shorter distance in the same amount of time. All right, so now let's actually do the calculation. So it says we're going to calculate the magnitude of the displacement for each one. So pause the video, go ahead and do that using whatever equations you like. Okay, so I want to use one of the easiest equations. I'm going to take the average velocity equation, v bar equals delta x over t, rearrange for delta x as delta x equals v bar t. Now there's other ways you could do it. You can do v naught t plus half at squared if you'd like to, but that would require finding the acceleration, which, you know, have in letter A, we'd have to find in letter B, but this one I think is easy because v bar is the average speed, and well, when time equals 0, the car is moving at 15 meters per second. At the end, the car is moving 15 meters per second. In fact, the car is constantly going 15 meters per second, so the average speed is just 15 meters per second for the entire run, and so it's going to be 15 meters per second times 4 seconds. We're given 2 sig figs in the time, so we have 2 sig figs in our answer, and you probably don't even need a calculator, but certainly you could use a calculator if you'd like to. Calculate this at 60 meters. Great. For car B, well, I'm going to do the same thing. I'm actually going to use delta x equals v bar t, although there's other options here. But I'm going to do this because, you know what, finding v bar still isn't going to be very difficult. In this case, I just want to take the average of the initial and the final speeds. And you can just read the graph. With at 0 meters per second, at 0 seconds, this car is moving at 0 meters per second. At the 4 second mark, the car is moving at 15 meters per second. We can do the average of 0 to 15 in our heads, but again, if you want to use a calculator, you can. We know the average speed is going to be 7.5 meters per second times 4 seconds. Maybe you need a calculator for this one. Maybe you can do it in your head. In the end, though, we should be getting 30 meters. And certainly, this agrees with our original assertion that car A should go farther than car B. Literally, it goes twice as far. Which, again, should make sense because car B takes time to speed up to the same final speed that car A had. Okay, so that's nice. Well, what can we learn from this? Well, let's just, recap a little bit of some of the things you've already picked up when you were learning about graphical analysis. All right, so I'm going to start to talk about some of the things we should already know. First thing is that we had straight lines on both of those, and that's telling us some information. So first of all, the slope of a graph and the shape, in this case the straight line, have meaning. The slope we can figure out by looking at the units of the slope or figuring out what we divided to get that, but the shape is also telling us something, because once we know what the slope represents, what is happening to the slope determines the shape of the graph. So let's first talk about the fact that we got straight lines, and straight line means that it has a constant slope. So we'll say the slope of any straight line has a constant value. No matter where you take the slope of a straight line, you're going to get the same number, no matter what 2 points you pick, because slope is steepness, and a straight line has a constant steepness. In fact, the mathematical definition of a straight line is a curve with constant slope. It never changes, right? So that's rather important. So then once we figure out what the slope represents, if we have a straight line, we know that that quantity has a constant value. And this is why we graph things. We graph sets of data because it will often reveal things that just the set of numbers can't really tell just by looking at it. Now, specifically, we're looking at, originally in other problems, we're looking at position versus time graphs, and of course we know the slope of position versus time represents velocity. And there's really no magic to this, right? If you look at what you're doing and you find slope, you're doing a rise over a run. You're doing a delta x over a delta t. And, well, delta x over t, that's the equation for v bar, right? Which is average velocity. So technically, when we have a straight line, you find the slope, you're finding the average velocity. But if you were to take really, really short time intervals, you can imagine you're taking the instantaneous velocity. It's just that for a straight line that has a constant slope, it has a constant velocity for its value there for position versus time, which means that all those points have the same value, and so the instantaneous velocities are equivalent to the average velocity. If the shape were of a changing slope, then you would take a tangent line to the curve there, you take the slope of that tangent line, and that would represent the instantaneous velocity at that one point. That's getting a little bit more of calculus ideas, but it bears mentioning here. These graphs we're looking at in problem 7, though, were velocity versus time graphs, and so when you take the slope of that, what could that possibly represent? Well, think about it, right? You're taking a change of velocity over a time. Well, delta v over t, that's the equation, of course, for acceleration. A equals delta v over t, literally the rise over the run for this type of graph. And so we can see that the slope velocity versus time represents acceleration. It literally links to the equation. So it's not magic to try to figure out what the slope represents. You literally just take the quantity on the rise and divide by the quantity on the run and then match it up to an equation you already know. And if things are lining up, there's a really good chance that you've figured out what the slope represents. And then once you know what the slope represents, you can link it to the shape of the graph. So for example, here where we have a horizontal line, what's the slope of a horizontal line? 0, right? And of course, it was never speeding up or slowing down. It had a 0 acceleration, so that makes sense. Here we have a straight line with a positive slope, right? And that's telling us that the acceleration is a positive value, which meant it was increasing its speed, which of course we can see here. But also that means that no matter where we take the slope, we're going to have the same value of the slope, which means this is a constant positive acceleration. And then if either one of these graphs were curved, that would mean it would be a changing slope. That would be a changing acceleration. We don't really deal very much with changing accelerations at this level, but certainly it could happen, and now you would know how to analyze such a thing. But let's now take it from a slightly different perspective. Let's go back to the graph here for car A. When we found the displacement, we took v bar times t, and v bar was the 15 meters per second, and t here was the 4 seconds, and so we're literally multiplying this dimension of the graph by this dimension of the graph. And if you look at this from sort of a geometric perspective, you can see that this dashed line at the 4 second mark sort of bounds a shape under the curve, that shape being a rectangle. And by doing 15 by 4, what are you actually finding about that rectangle? Well, you're finding the area, aren't you, right? Length by width, 15 by 4, and by doing so, we found the displacement. Well, let's look over here. If you're taking a look at the line here represented by the changing velocity, which is bounded by the 4 seconds and the 15 meters per second, when we did delta x equals v bar t, well, we took the average velocity, the average of 0 and 15, multiplied by the time, and if the same idea should hold, that means we should have been finding the area under this shape. Well, this shape is a triangle, and area of a triangle is half base height, and oh, the base is 4, the height is 15, we took half of 15 to get 7.5, and look what happened here. Lo and behold, when you find the area of that triangle, yeah, we found the displacement as well. And so now we can also realize that not only does the slope of a graph often have meaning, the area under the graph also often has meaning. So let's go back to this listing of these connections. We're going to say that the area on a velocity versus time graph represents displacement. And if you're looking back at graph A and you found delta x equals v bar t, you literally just take this equation and multiply t to both sides, and you have the equation for what was the area under there. Now, I'm saying area under, it's really the area between the line and the horizontal axis, which means that if there's area above the horizontal axis, that would represent a positive whatever it is you're looking at. If there's area below, that would be a negative whatever it is you're looking at. And when I say whatever it is you're looking at, I want to leave it generic because every graph, well, the area will represent something different. In fact, sometimes the area won't represent anything in terms of a physical quantity, but if you line it up with the units involved or with some equation, there's a really good chance that you've discovered what the area represents. When we're dealing with kinematics graphs, these three graphs, position versus time, velocity versus time, and then acceleration versus time, are the three ones that we look at most often. So I'm going to just show you a great way to remember the connections among them. So let's say you're given a position versus time graph and want to get some information about the velocity. Well, what are you going to do? We've already shown, and we have it right here, that if you were to take the slope of that graph, that's going to give you information about the velocity. If it's a straight line, it'll give you the average velocity, which is also the instantaneous velocity, since they're going to match, since if a straight line has a constant slope. If it's a curved line, then again, you would take the slope of that tangent line, that would give you the instantaneous velocity at that moment. But it's always going to be the slope. Okay, so what if you have a velocity versus time graph and want to find information about the acceleration? Well, we know what that's going to be as well. You're just going to find the slope again. So it's sort of like going up one more level. Those of you who have maybe already taken calculus will learn another word for this. This is called taking the derivative. And those of you who have not taken calculus, you don't have to worry about that. We're just sort of planting a seed so that later on when you eventually take calculus, you'll say derivative. Oh, okay, that's just like a fancy term for taking the slope. So you already know a little bit about that. All right, well, let's say you're given a velocity versus time graph, and instead of finding acceleration, you want to find some information about position. What should you do? Well, we just showed that this is going to be the area. That's going to represent, well, not position, it's really going to represent displacement, which is the change in position. So it's not going to give you where the object is, it's going to tell you how much the object has changed in its position over that time interval. So, let's say you're given an acceleration versus time graph, and you're tasked with finding some information about velocity. By symmetry, what do you think you should do? Well, hopefully you see all the symmetries in this graphic organizer. If you find the area under that graph, you're going to get some information about velocity. But be real particular here. You're not going to get velocity. What are you actually going to get? Can you see all the parallels? Can you see the symmetries? It's right here. Hopefully you see that here, when we took the area under velocity versus time, we got delta x. So here when we take the area under acceleration versus time, we're going to get delta v. So not the velocity, but the change in velocity. And if you're not quite sure about how that works, we can go right back to this equation here. If there were a rectangular shape on the graph, you'd be multiplying acceleration times time. You can see the equation then says you're really getting the change of velocity. You're getting delta v, not v itself. So this little graphic organizer here is a great way to remember all these connections among the kinematics graphs. And just one more seed I'm going to plant here. Those of you who are eventually going to be taking calculus, there's another word that goes along with finding the area. That's called taking the integral. You're going to be integrating all the bits of area under the graph, even for a curved line. That's going to get you the information here. And again, you're not really going to see that until you get to calculus, but eventually when they mention the idea of taking the integral, you can say, oh yeah, I learned something about that back in AP Physics 1. That's really taking the area under the graph.